Okay, fine. Let's get on with the class. So, yeah. So, I think so far we have been focusing more on CRE1. So, I think we started with the basics of kinetics. We looked at the different reaction rates and reaction equations, rate constants. Then we looked at into various theories like Arrhenius theory for temperature dependency. We derived equations, rate equations for various kinds of reactions and so on. And then we moved on to ideal reactors. So basically, batch, PFR, and CSTR. We looked into like how we can uh, derive the equations or like the basic design equations for these reactors, how we can represent their conversion, those kinds of things graphically. So we looked into those kinds of things with regards to ideal reactors. Then then we looked into some concepts like multiple reactions, like basically reactions in series and parallel. Then some special kinds of reactions like autocatalytic reactions, then, reversible reactions, cyclic reactions, and so on. And then I think we looked into recycle reactor. I think this is one of the latest topic we looked into, I think. So recycle reactor and yeah, this is pretty much some of like the most of the basic concepts when it comes to chemical reaction engineering one. So CRE2 is probably next in course for us. CRE2 like basically deals with non-ideal reactors, and it also deals with catalysis. So like these are the two main topics in CRE2. So we'll look into that. But before we move on to CRE2, what I want to do is we'll spend one or two classes just going through some of the leftover gate questions from previous year gate, and yeah, let let's see how we can proceed. And also, if you are also doing it on your own, just see if you have any questions that you are having doubts when it comes to solving these questions. Just mail the questions to me, and we can also look into those questions in the coming classes. All right. So let me, yeah. So yeah, let's just get on with the questions. Let's just go through this question. It is pretty straightforward, simple question. Just go through it. We'll see how we can solve it in a minute. Okay. Okay. So this is a question from GATE 2018. Question number 39 from chemical engineering. A CSTR and PFR of equal volume are connected in series as shown below to carry out a first order isothermal liquid phase reaction. The reaction is A giving B. The rate constant is 0.2 second inverse. The space time is 5 seconds for both the reactors. The overall fractional conversion of A is dash rounded off to third decimal place. So this is a question from reactors in series, and the NPTEL reference can be found in module 1, lecture 27, PFR and MFR in series, chemical reaction engineering 1, homogeneous reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So here we have a system, a series system. The system first starts with a CSTR with an initial concentration Ca0, and let's say Ca1 is the outlet concentration of the CSTR, and this Ca1 enters the PFR, and the outlet concentration of PFR is CAF. The reaction that happens here is basically A giving B, which and based on the value of the reactant rate constant, which is 0.2 second inverse, this is a first order reaction. So what we need to find here is the overall fractional conversion. That means the conversion from Ca0 to CAF. What is the conversion for this? So one more data they have given is that the space time for both the reactors. So CSTR, the space time is 5 seconds, and for PFR also the space time is 5 seconds. So using the data that they have given us, we need to find the overall fractional conversion. So let us first take the CSTR system. So we have a CSTR, and Ca0 is the initial concentration, tau is 5 seconds, and we said that Ca1 be the outlet concentration. So by design equation of CSTR, we can say tau, which is equal to Ca0 into Xa by minus Ra. So tau here is basically given as 5 seconds. So 5 is equal to Ca0 into Xa by minus Ra. So this minus Ra is Kca because this is a first order reaction. So we can write it as Kca, and this Kca can again be written as K into Ca0 into 1 minus Xa. So K Ca0 into 1 minus Xa. So the Ca0 and Ca0 will get cancelled, and it is given that the K is 0.2. So 5 is equal to Xa by 0.2 into 1 minus Xa. We need to solve this to find Xa. So if we solve this, this is a simple solving. We'll get Xa as 0.5. So what this means is basically Ca1 is basically 0.5 Ca0. Now let us move on to the next case, which is the PFR that is connected in series. So the entry of this PFR will be Ca1, and the exit will be CAF. And here also the space time is 5 seconds. So here also we can apply the design equation. So the design equation will be tau is equal to integral of CA0 to CA minus DCA by minus RA. So this will be the design equation for PFR. So again, tau is 5 seconds. We can substitute that. And this RA, we can write it as KCA because it is a first order reaction. So tau will be dCA by minus RA, and if we integrate it, it will be 1 by K ln CA0 by CA. Now here, this CA0 is basically CA1, or like to avoid confusion, I'll just so what I'll do, I'll use the proper notations. The notation got changed a bit. Okay. So the design equation for this PFR will be tau is equal to integral of CA1 to CAF minus DCA by minus RA, and this minus RA will be KCAF. Right? So we can uh, we can integrate this equation, and we can also substitute tau as 5 seconds. We'll get 5 is equal to 1 by K ln CA1 by CAF. Now K is given as 0.2. So if we substitute for K and rearrange it, we'll get 1 is equal to ln CA1 by CAF. Now we'll take exponential on both sides. So taking exponential on both sides, E will be equal to CA1 by CAF, and the value of E is 2.718. So what this means is CA1 by CAF is equal to 2.718. Also, from the CSTR case, we established that CA1 is equal to 0.5 CA0. So using this, we can derive a relationship between CAF and CA0, because CA1 by CAF will be 0.5 CA0 by CAF, and that is equal to 2.718. So CAF will be 0.5 CA0 by 2.718, and that will be approximately 0.184 CA0. So now we have all the data required to find the overall conversion. So the overall conversion XAF will be equal to 1 minus CAF by CA0. So we have CAF in terms of CA0. So we'll substitute that here. So XAF will be 1 minus CAF, that is 0.184 CA0 by CA0. So CA0 and CA0 will get cancelled, and this will be 1 minus 0.184, and that will be 0.816. So this is the overall fractional conversion for this question. The right answer will vary between 0.8 to 0.89. Okay. Um, yeah, so this is, basically just a straightforward application of the design equations. So because we don't have all the values here, we'll have to take a lot of variables. So for example, the CA0, CA1, we don't have the values for this. So we'll have to take variables and do it. Or what you can also do is you can just take an assumption, like assume a value for Ca0. So if you take Ca0 as 1 mole per meter cube or something, you can directly get values and you will get the same answer again. The fractional conversion XAF as point 816, or like depending on the accuracy, it will be varying between zero point 0.8 to zero point 0.9. So yeah, so that is one way to do it. So one way is, as I just showed before, you just take the variable as the variable. So here we took the CA1 and CAF as terms depending on CA0. So we represented CA1 and CAF in terms of CA0, and then we just cancelled out that CA0 term in the final calculation of the conversion. If this is a bit complicating, what we can do uh, otherwise is just assume a value for CA0 and then follow the same steps. So you assume a value for CA0, apply the design equation for CSTR, we find find the concentration outlet from of the outlet of the CSTR CA1. So CA1, we got it as zero point 0.5 CA0. So we'll get the CA1 as zero point 0.5 mole per meter cube. So now using this CA1, and you can apply the design equation for the PFR now, using CA1 is equal to zero point 0.5 as your initial concentration. And again, you can find the outlet concentration of the PFR, which will be CAF. And that you will get it as 0.184. And based on this we can calculate the fractional conversion again, right? Is this clear? Okay. Okay, so if the okay, fine, let's move on to the next question. So this is a question from gate 2018 from chemical engineering, question number 40. The elementary second order liquid phase reaction A plus B giving C plus D is carried out in an isothermal plug flow reactor of 2 meter cube volume. The inlet volumetric flow rate is 10 meter cube per hour. The initial concentrations of both A and B are 2 kilomole per meter cube, and the rate constant is given as 2.5 meter cube per kilomole per hour. The percentage conversion of A is dash. So this is a question from ideal reactors part in chemical reaction engineering, and the reference NPTEL series can be found in module 1, lecture 14, design of plug flow reactors part 1, chemical reaction engineering 1, homogeneous reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So here in this question, let us first represent the data given to us. So we have a PFR, and inside the PFR there are two reactants here, which are A and B, with initial concentration Ca0 is equal to 2 and Cb0 equal to 2. And the outlet will consist of Ca, Cb, and the products Cc and Cd. Now the flow rate nu is given as 10 meter cube per hour, and the volume of the reactor V is given as 2 meter cube. So using these data, we need to find the percentage conversion, which is XA in percentage. So what we can do here is we can start with the design equation of the PFR. So the design equation of PFR is basically tau is equal to V by nu, which is equal to integral minus dCA by minus RA from CA0 to CA. So here minus RA will be K CA CB, because in the question it is given that the reaction is a second order elementary liquid phase reaction. So minus RA will be KCACB. So we can substitute that in the design equation, and we also have the values for V and nu, which we can also substitute in the design equation. So if we rewrite the design equation, it will be 2 by 10 is equal to integral CA0 to CA minus dCA by K CACB. So here we can note that inside the integration there are two concentration terms, Ca and Cb. So let us see how we can deal with these two terms. So let us take a scenario. Let's say at time t equal to 0, we have the four elements, the two reactants and the two products. So at time t equal to 0, the concentration of A will be Ca0, which is 2, and concentration of B will be Cb0, which will be also 2. At time t equal to 0, since the reaction does not happen yet, the concentration of C and D will be 0. Now let's say at time t, where let's say our required fractional conversion has already happened. So that means, let's say X amount of reactants have reacted to form X amount of products. So the concentration of A at this time Ca will be equal to 2 minus X. And similarly, concentration of B will be equal to 2 minus X. Because we just said that X moles of A and X moles of B will react. Because the stoichiometry of A and B are same, whatever amount of A is reacting, B will also react. So let's say if out of the 2 moles of A, 1 mole of A is reacting, then 1 mole of B will also react to form the products. So the concentration of A and concentration of B both will be 2 minus X after time t. And after time t, the moles of products will be X and X. That means X amount of C and X amount of D, or X moles of C and X moles of D will be formed after time t. So what we are trying to show from this balance is that once the reaction happens, or at time t, concentration of A is basically equal to concentration of B. So we can substitute this concept into our design equation. So in our design equation, we had 2 by 10 is equal to integral Ca0 to Ca minus dCA by KCACB. We can write the CACB as CA square itself, because CB is equal to CA as just what we have established so far. So this will be Ca0 into Ca minus dCA by kCa square. So this will be our new design equation with only Ca term in our design equation. So now we can proceed easily and using the direct integration itself. So 2 by 10 will be equal to 1 by k. Integral of dCa by Ca square will be minus 1 by Ca, and applying the limits it will be 1 by k into 1 by Ca minus 1 by Ca0. Also in the question it is given that k is equal to 2.5. So substitute these values and just find the value of Ca. So we have k is equal to 2.5. We also have Ca0 is equal to 2. Substitute these values. We'll get 2 by 10 is equal to 1 by 2.5 into 1 by Ca minus 1 by Ca0, which will be 2. So rearranging this, 1 by 2 is equal to 1 by Ca minus 1 by 2. Or in other words, Ca will be equal to 1. So now we have Ca is equal to 1. We also have Ca0 is equal to 2. So the percentage conversion will be 1 minus Ca by Ca0 into 100%. And this will be 1 minus 1 by 2 into 100, which will be 0.5 into 100, or basically 50%. So the percentage conversion in this system is 50%. Right. So here also basically what we have done is just apply our design equation for PFR. The only thing or the only modification that we are trying to do here is with the equation for the reaction rate. So A plus B giving C plus D, the reaction rate equation will be KCACB. And since the stoichiometry of A and B are same, we can assume that KCACB will be approximately equal to KCA square. So now our design equation will only have Ca term, and then from then onwards it is just a straightforward integration and applying the limits and then solving for Ca. And once you find Ca, the final concentration of Ca, we can use that Ca and Ca0 to find the percentage conversion, which will come to 50%. Okay. Okay. So if there are no doubts, we can move on to the next question. Okay. So this is a question from GATE 2018 from Chemical Engineering, question number 51. A set of standard stainless steel pipes, each of internal diameter 26.65 millimeter and 6000 millimeter length, is used to make a plug flow reactor by joining them in series to carry out the degradation of polyethylene. 7 such pipes are required to obtain a conversion of 66% at 450 Kelvin. The minimum number of standard 8,000 millimeter long pipes of the same internal diameter to be procured for obtaining at least 66% conversion under the same reaction conditions is dash. So this is a question from ideal reactors, and the NPTEL reference can be found in Module 1, Lecture 13, Basics of Plug Flow Reactor Part 2, Chemical Reaction Engineering 1, Homogeneous Reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So here, in this question, it is said that they have used stainless steel pipes to make a plug flow reactor. So in the case 1, this is the dimension of the pipes they have used. So the inner diameter will be 26.65 mm and the length of the pipe will be 6000 mm. So they have joined 7 such pipes in series and they have made a plug flow reactor. Now what they are asking is, if instead of this stainless steel pipe, if they use a pipe having the same inner diameter but different length, which is 8000 mm, but everything else is the same. So basically the inner diameter will be 26.65 mm, and even the reaction conditions and the reaction, everything is same, even the conversion is also same. So what we want to find is how many of such 8000 mm long pipes will be required to achieve at least the same 66% conversion. So here basically the concept that we need to use is that since the reaction conversion is the same, the reaction conditions are the same, and the reaction parameters, everything with regards to the reaction is same, that means the volume should also remain the same in order to provide the same conversion. So if the reaction conditions are same, and also the conversion is also same, then the volume of the reactor should also remain the same. Okay, so using this, we'll try to see how we can proceed. So first, what we need to find here is the volume of the reactor, volume of our plug flow reactor, and it is given in the question that this plug flow reactor is made of 7 stainless steel pipes of the 6000 meter cube, 6000 millimeter length. So volume of this PFR will be 7 into volume of 6000 mm long pipes. Okay, so this will be 7 into volume of each pipe will be pi pi d square by 4 into length. So pi into d square, which is 26.65, the whole square by 4 into 6000. So if we do the max here, the volume of PFR will come to 2,3,4,2,7,912.778 millimeter cube. So this will be the volume of the PFR in millimeter cube. So now if we use 8000 mm pipes instead of the 6000 mm pipes, we need to find how many number of such pipes are required. So for that, what we can do is number of pipes, number of 8000 mm pipes will be equal to volume of PFR by volume of the 8000 mm pipes. Okay. So if we do this, we can find how many number of such 8000 mm pipes are required for this system. So we can find the volume of 8000 mm pipes as pi d square by 4 into h, which will be pi into 26.65 the whole square in by 4 into 8000. So if we do the max, we'll get volume of 8000 mm pipes to be 4462459.577 millimeter cube. So we already found the volume of the PFR as 234,27912.778 millimeter cube. So to find number of such 8000 mm pipes required, number of pipes required will be this volume of PFR by volume of the 8000 mm pipe. So this will be 234,27912.778 the whole by 4462459.577, and this will if we do the max, this will roughly come to 5.25. Now the thing to note here is that this mathematics says that we need 5.25 of such 8000 mm pipes, but practically taking a fraction of the stainless steel pipe is not ideal, or it is not practical. So what we have to do is we have to take the next integer of the value that we got as the minimum number of pipes. So we got 5.25 as our value. That means we need at least 6 of these pipes to achieve the conversion, which is 66% in this question. So the number of pipes will be 6 here. Okay. So there is not a lot of CRE concept in this question, to be honest. It is basically simple mathematics in this question. So basically what they have given us is that there are two kinds of pipes that you can use to construct PFR. So case one is where the length is 6000 millimeter, and case two is where it is 8000 millimeter. So if you need 7 such pipes of 6000 millimeter, how many pipes do you need if the length is 8000 millimeter? So, you know, because we just said that the reaction conditions and reaction conversion, everything is the same. That means the volume should also remain the same. And using the volume of the PFR, we can find the number of pipes required to carry out this process. Is this clear? Okay. If there are no doubts, let us try to do one more question for the day. Just go through this question. Again, this is based on the basics of kinetics. Just go through this question. We'll see how we can solve this question in a minute. Okay. Okay. Sorry about that. Okay. So let's see how we can proceed with this question. So this is a question from GATE 2018 from Chemical Engineering, question number 52. Hydrogenation of benzene is to be carried out using nickel with a density of 8910 kilogram per meter cube as catalyst, cast in the form of non-porous hollow cylinders as shown below. The reaction occurs on all the surfaces of the hollow cylinder. During an experiment, one such cylinder is suspended in the reactant stream. If the observed rate of reaction is 0.39 mole per meter square of the catalyst surface per minute, then the rate of the reaction in mole per kilogram of catalyst per minute is dash rounded off to 3 decimal places. So there is a question from kinetics part in chemical reaction engineering, and the reference NPTEL series can be found in module 1, lecture 9, basics of kinetics and contacting, chemical reaction engineering 1, homogeneous reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So here in this question, they are trying to carry out a reaction using a catalyst by dipping this catalyst into the reaction stream. So here this catalyst is basically in the form of a hollow cylinder with the dimensions as given here. They have also said that the reaction happens on all the surfaces of the hollow cylinder, and the observed reaction rate is given as 0.39 mole per meter square of catalyst surface per minute. What we need to find here is the same rate of reaction for this process, but in terms of mole per kilogram of catalyst per minute. So basically what we are trying to do here is convert this reaction which is given in mole per meter square catalyst per minute to mole per kilogram of catalyst per minute. So let us see how we can do this. So here again the reaction rate is given as 0.39 mole per meter square catalyst per minute, and we need it in terms of mole per kilogram catalyst per minute. So that means we need to somehow convert this meter square term into the kilogram term. So how we can do is, let us just write the units: meter square catalyst per minute. Now if we multiply this by kilogram catalyst and then divide it by meter square catalyst, then we'll get the new unit as mole per kilogram catalyst per minute, right? Because this meter square catalyst and meter square catalyst will get cancelled. So basically what we need to do here is we need to divide the reaction rate that we have been given by a term which has a unit kilogram of catalyst per meter square of catalyst. Or in other terms, we need to divide our reaction rate by weight per surface area of our catalyst. So if we divide our given rate by weight per area of the catalyst, we'll get the required reaction rate in terms of mole per kilogram catalyst per minute. So let us see how we can find this weight per area of the catalyst and finally see how we can find the final answer. So to find weight per area of the catalyst, we need two things, which is obviously the weight of catalyst used and the surface area of the catalyst used. Let us start with the weight of catalyst used. So weight of catalyst used W will be equal to density into volume of catalyst. So here they have given that the density of the catalyst is 8910 kilogram per meter cube. And the catalyst is a hollow sphere and the dimensions are also given. So we can use these dimensions and the fact that the catalyst is a hollow sphere, and we can find the volume of the catalyst. So volume of the catalyst V will be the formula for volume of a cylinder will be pi d square by 4 into h. So we'll just use this formula to find the volume of the catalyst. So this weight will be 8910 into volume of the catalyst. So this is a hollow sphere. The outer diameters are given as 25 and the inner diameters are given as 20. The height is also given as 25. So volume of a hollow sphere will be pi into h into d square by 4 minus small d square by 4, where this capital D is 25 mm and small d is 20 mm and the height h is 25 mm. So weight of the catalyst W will be 8910 into pi into 25 mm, which is 0.025 meter, by 4 into d square. So 25 mm square, that will be 0.025 square minus 20 mm square, which will be 0.02 square. So if we do the math here, we'll get the final answer for weight in terms of pi as W is equal to 0.01253 into pi kgs. Now let us move on to the area of the catalyst. So area of the catalyst. So again, this is a hollow sphere. So here there are four areas here. One is the outer area, then there will be an inner area, and then there will be two more areas, which are the areas at the top ring and the bottom ring. So area of the catalyst will basically be outer surface area plus inner surface area plus top ring area plus bottom area. So area of catalyst A will be outer surface area. For a cylinder, the area can be calculated as pi d into h. This will be the area of a cylinder. So for outer surface area, it will be pi into capital D into h plus inner surface area, which will be pi into small d into h plus top area and bottom area will basically be the same. So we can just write it as 2 into top area, which will be the area which is in the shape of the ring. So that will be pi into d square minus small d square by 4. So here capital D is basically 25 mm, small d is 20 mm and h is 25 mm. So this will be pi into d, which is 25 mm or 0.025 meter, into height, which is again 0.025 meter, plus pi into d small d, which is 0.02 meter, into height, which is 0.025 meter, plus 2 into pi d square, that is 0.025 the whole square, minus small d square, which is 0.02 the whole square, by 4. So if we do the math here, we'll get an area in terms of pi as 0.001235 into pi. So now we have W, we have A. So now we have W as 0.01253 kg and A as, sorry, okay. So now we have W is equal to 0.01253 into pi kg and A, which is 0.0012375 into pi meter square. So W by A will basically be the ratio of this, and if we divide these two, the pi and pi will get cancelled, and if we do the math here, we'll get W by A is equal to 10.125 kilogram per meter square. So now our reaction rate in terms of kilogram per catalyst. So let us denote it as minus RA W. This will be the given reaction rate by W by A of catalyst. So this will be 0.39 by 10.125 kilogram per meter square of catalyst. And if we do the math here, we'll get the final answer as 0.0385. And since we need to approximate it in three decimal points, it will be approximately 0.039, and the unit will be mole per kilogram catalyst per minute. The right answer will vary between 0.034 to 0.043. Right? So this is like just converting the units of our reaction rate to kilogram catalyst from meter square catalyst. So I hope you guys understood the conversion basically. So this is the conversion here. So what we are doing is we are trying to convert a reaction rate given in terms of mole per meter square catalyst per minute to mole per kilogram catalyst per minute. And to do that, all we need to do is just divide our given reaction rate by weight by area of the catalyst. So the units of meter square will get cancelled and we'll get a different reaction rate with the unit mole per kilogram of catalyst per minute. So we just proceeded in that direction, and based on the data that's been given to us, so they have given us the density of the catalyst, they have given us the dimensions of the catalyst. We can find the volume with which we can find the weight of the catalyst, and then using the dimensions of the catalyst, we can find the area of the catalyst, and their ratio will be the weight by area of the catalyst. And once we find the weight by area of the catalyst, we just divide it with the divide it to the divide the older reaction rate or the given reaction rate by weight by area, and finally we'll get our required answer here in the unit of mole per kilogram catalyst per minute. Right? Okay. If this is clear, then we'll stop for today at this point. So any doubts with regards to any of the questions discussed today? Okay. So, okay, fine. We'll just stop here for today. And yeah, I'll see you next Monday.